So where we're starting out at is we've finished up with first order. And there is something special about first order in that there's certain techniques that work for first order. So when we have first order differential equations, we have better tools, at least a more refined tool set. When we start moving into higher order differential equations, we don't have quite the same set of tools. So for example, there's nothing like exact differential equations as one example. And integrating factors are, basically they don't exist unless by some weird fluke you have just the right thing, which of course you would never have just the right thing. So we have to sort of say, okay, where are we at now? What can we do? So we're going to start with our terminology so we understand how to communicate what's going on. So now we're dealing with higher order. So we say a differential equation is an nth order. So remember we talked about order of derivatives. So nth order tells you how big is the largest derivative. So the highest derivative, so in this case it's the nth derivative, is the order. And the key word that I want to highlight here is linear. And we've talked about linear first order equations. And so what does it mean to be a linear nth order equation? Well, it says we have some function times the nth derivative, some function times n minus first derivative, and so forth and so on, all the way to some function times just the function equals f of x. And these pieces in front, the an of x, an minus 1 of x, so forth and so on, all the way down to the n, they can be really exotic functions of x, but only of x, and that's the whole point. They're not things where you have functions of combining x and y prime. They're just functions of x. And this other side, f of x, again, can be any function you want. So suppose we say, look at this differential equation, y double prime plus y squared e to the x equals tangent of x. Is this linear?
Yes. No.
Okay, we've had some person say yes, and then the same person said no. They're both right and wrong. Is there another person who?
Yes, it is linear, I think.
Okay. Do you also want to say no just to follow the crowd?
No, I'm good.
No, you don't want to say no? Look at this part. What do you see? Y squared. Now, when we talk about linear, linear says you can only have the function and derivatives, but you can't have things meshing together. So you can't do anything to your function. You can't put it inside of anything. You can't take y times y prime. It always has to be just either the function or one of its derivatives by itself. So this y squared says this is not linear. How about this one? So e to the x, y triple prime, which is the third derivative, minus x over x squared plus 1y double prime, plus sine of xy equals 4. Linear? Not linear? Now there's lots of really crazy functions here. Are you sure you want to say linear? Yeah. See, those crazy functions are the functions of x. When we talk about linear, we're talking about it in terms of how is it in regards to y and the derivatives of y. So this is linear. Even though you have weird functions, that's no problem. Now you might notice, hey, we skipped y prime. Is that a problem? No, it's not a problem. What is y prime, how do we think of it as in this case? Yeah, 0 y prime. So it's okay if you're missing derivatives in the middle. No problem, no problem. Okay, so that's linear. And we've talked about first order linear, so essentially this is just a generalization of that. And we like linear. Linear is really good for us. Linear is our friend, and we'll talk about that as we go on. The next concept is what we call homogeneous versus non-homogeneous. Now here we run into a small sort of like, we've said homogeneous in a certain context when we talked about our first order differential equations. And this is a completely different interpretation of the word homogeneous. And I apologize, we ran out of words and notation about 100 years ago in mathematics, and we had to start recycling. So unfortunately, sometimes we use the same word to describe different things. But the key here is to say, what's happening with that right-hand side? What's happening to f of x? So if f of x is 0, that would be called homogeneous. If f of x is not 0, then it's non-homogeneous. So, for instance, I have some equations here. This equation, that's supposed to be a y prime. Homogeneous or non-homogeneous? Yeah, non-homogeneous, because you see, this part is not 0. How about here? Yes, this is homogeneous. Even though you have, functions over here where you have, crazier functions of x, the homogeneous, non-homogeneous, all is about that right-hand side. What do you have? Is it 0 or not 0? All right, so that's another term. And then the last piece of terminology is we say a differential equation has constant coefficients. All right, now here's a case where the terminology is very descriptive. It has constant coefficients if the coefficients are constants. So that's how you can remember what's going on. So in other words, these pieces in front of your derivatives are numbers. They don't vary with x. Now, there's no restriction on the right-hand side. It's all about the coefficients in front of y and the derivatives of y. So, for instance, here is something. Fourth derivative of y minus 3y double prime plus 2y prime plus 4y equals 0. All of these coefficients are constants. So this is a constant coefficient differential equation. Are there any others? That's also a constant coefficient. Now you might say, wait, what about the e to the x? Well, that's the other side. That's f of x. The coefficients of the y's and y primes and y double primes, those are constants. So it's okay that f of x is more exotic. We still call it constant coefficient. Now you might say, Steve, which differential equations do we like? In fact, there's an answer. So what do we like? We like things which are linear. And we like things which are homogeneous. And we like things which are constant coefficient. So if you put all of these together, that gets us a nice differential equation. And we say that that setting is love. We love it. Because that is something that we have the technology. We have the tools. Now, you might think we don't have the tools, but that's going to be in our next set of lectures. We're going to go through and say, look, we can solve these. We have perfect tools to solve it. All right, so any questions on our terminology? Good. Well, now that we can talk about things, we come to two important ideas. And the first important idea is this notion of existence. Because we like to say, hey, is there a solution that we can even find? Does it exist? And is there just one or are there many? That's the uniqueness. So it turns out that suppose we have our differential equation and we make our leading coefficient a 1. And we have some initial conditions. So how many initial conditions? Well, you'll see here, it's an nth order derivative. And so we're going to have n initial conditions. So we need enough information to tell us how to get going. So you can actually count, because you see we have the value of the function at a point, the value of the derivative at that point, all the way up to the value of the n minus first derivative at that point. Now you might be thinking, wait a second, n minus 1, aren't you missing something? Shouldn't we have n? Well, we started at 0. So there are, in fact, n pieces of information here. All right. So if we have a reasonable differential equation, nth order, we have n initial conditions, then it has a unique solution as long as the pieces are continuous. So And so in other words, you can extend it as far as the pieces are continuous. You can't be guaranteed past that. But we just care that we can extend it a little bit. As long as it exists a little bit, then we're okay. This should feel very familiar because it's essentially the same thing that we said for first order differential equations. We're just saying it's essentially the same idea. We can't extend it. Now, unfortunately for first order, we had a nice argument that says, and here's how you find the solution. And then we went into integrating factors. Unfortunately, there's not a clean argument that we have for this, but it's still a true statement. It just requires more machinery than what we are capable of producing right now. So we're going to just take it on faith. All right, so that's the first idea. We have solutions. Now the second idea, this is good. This is superposition. Now this is an interesting word, superposition. And there's a couple of places it shows up. It's used in geology, for instance. And what I like to think of superposition as is sort of an idea of stacking, or if you like, combining. And what we want to do is we want to put solutions together. So here's what it says. Suppose you have some solutions. So we have some set of solutions to our homogeneous differential equation. And, well, notice what kind of differential equation is this? It's homogeneous. What else is it? There's another key word. What? Linear. Yeah. It's a linear differential equation. Okay, so we have this nice homogeneous linear differential equation. And we have some solutions. And it says, you know what you can do with those solutions? You can make new solutions. And you can make new solutions in a very simple way. So in other words, the simple way is you take some constant times your first function, a different constant times your second function, all the way up to some final constant times your final function. Add them all together. And regardless of what your constants are, the result is also a solution to your differential equation. All right. Now, let's pause here and say, you know, this part right here says we're finding a certain type of combination of our functions. So there's a certain key word that goes along with what's happening here, where we're multiplying by numbers, adding them together. What do we call that when we're doing that? Scaling by numbers, adding together. We call that a blank combination. You fill in the blank?
Linear.
It's a linear combination. What? The word linear showing up again? Oh my gosh. It's a sign. It's a sign. Okay. So if we have a linear differential equation, which is homogeneous, then that says you can take linear combinations of your solutions and keep finding new solutions. Now, we're going to argue why this is true, or at least get some intuition about why this is true. Okay, so let's work through a simple case. The general case is the same type of argument. So suppose we're dealing with the case where we have a second order. So say y double prime plus a1 of x, y prime plus a0 of x times y equals 0. So I'm just doing a second order, and we'll demonstrate it. And let's suppose we have two solutions. So we'll say that y1 and y2 are solutions. Now, when we say something is a solution to a differential equation, what does that mean? If I say, you know, x cubed is a solution to this differential equation, what does it mean to say x cubed is a solution to the differential equation?
If you plug in y equals x cubed, and then you take like the double derivative of y and the single derivative of y, and you put it all in there, then the equation still stands.
Yeah. Yeah, so to say something is a solution to a differential equation says, if I replace y by y1, or I replace y by y2, since they're both solutions, that relationship is satisfied. That equation works. So in particular, when I'm saying that y1 is a solution, what I can phrase it as is to say, oh, that means that y1 double prime plus a1 of x y1 prime plus a0 of x times y1 is equal to 0. And I can say, oh, since y2 is a solution, I can say y2 double prime plus a1 of x times y2 prime plus a0 of x times y2 equals 0. In other words, as was said, we can take these functions, plug them in, we get solutions out. Okay. So now we're going to come up with a new solution. All right. We'll give it a name. Let's call it capital Y. So capital Y is, I'm going to take some constant, I'll use c times y1, plus some other constant, I'll use d times y2. So I'm doing a linear combination of these two. And the goal is to say, now, show that y is a solution. That's our goal. So, how do we show something's a solution? Well, we just plug it in and verify. Okay. So we're going to take y double prime plus a1 of x, y prime, plus a0 of x, y. Okay, well, we're going to need to look at y prime, so let's do that really quickly. What is y prime? Well, c y1 prime plus d y2 prime. And we'll also need y double prime. Yeah, c y1 double prime plus d y2 double prime. Now, on a side note, we're actually using an important idea. So there's two key ideas why this works. So this is key idea number one. So I'll put a little star here. Key idea number one, derivatives are linear. So in other words, that says, hey, derivatives like to handle addition very easily. If I want to take the derivative of two functions being added, I take the derivatives of each function individually and add the result. If I have a number times a function, I'm taking that derivative, take the number times the derivative of that function. So derivatives are linear. That's essentially why it's so easy to take the derivatives for y here. So now we'll replace what everything is. So we say, okay, well, y double prime, no problem. That's c y1 double prime plus d y2 double prime. Then we have plus a1 of x, c y1 prime plus d y2 prime. And finally, we have our a0 of x, whoops, a0 of x, fancy a there. A0 of x, c y1 plus d y2. Okay. So I put in what the pieces are. Now let's group. Let's pull out everything with a c. So I'm factoring a c out. What has a c attached to it? So we just scan along. There's a c. So y1 double prime. Okay. Oh, there's a c. What will that be? y1 prime times a1 of x. Okay, and there's one more. y1 times a0. Okay, plus, we'll do the same thing for d. It's very similar. There's a y2 double prime. Then there's a plus a1 of x, y2 prime. And then there's a plus a0 of x, y2. And here what's happening is this step is because the differential equation is linear. It's set up in a nice way, so we're doing it, it's linear. Now, can we say anything about this piece, y1 double prime plus a1 of x, y1 prime plus a0 of x, y1? Other than it looks like a lot of alphabet soup. It equals 0. How do we know? Because we wrote it. We said it equals 0. That was our assumption. It says, oh, this piece came from a solution. So this equals 0. How about this other piece? Also equals 0. So we end up with 0 plus 0. But that 0 plus 0 equals 0. And now you're wondering, hey, what was that second fact that we needed? Well, here was the second fact. 0 plus 0 equals 0. It has that magical property. And now that's the verification. We've done it. We've shown y is a solution. Check. So that says we could combine. And this same idea carries over. That's why it works. It's because the pieces are linear. The taking derivatives are linear. We're starting with a linear differential equation. And if you add 0 a bunch of times, you get 0. That all combines to show why this idea of superposition works. Well, this is great. This says if we have solutions, we can make more solutions. But now there's this really cool statement, and we haven't said it yet, but it's an important statement. It says, suppose you have n solutions. So notice, I really want to point out that this n here says that you have n solutions, and it matches the order of the differential equation. So that says we have n solutions. But not only do we have n solutions, they're this linearly independent solutions. And I'm going to come back and talk about linearly independent in just a second here. The punchline is all solutions. Any solution that you have is some linear combination of those n solutions. All right. So that's really great news for us. Now, of course, you have the question, what does linearly independent mean? That's a great question. We're going to actually do that later today. But for our purposes, you should think of linearly independent as saying fundamentally different. So we want to have a group of solutions where essentially each solution is giving us something new. So there's no redundancy. So that's what we're trying to avoid. We say, we have this group of solutions. There's no redundancy among the pieces so that we capture everything. Yes?
I know we're going to talk about it later, but basically each linearly independent one can't be made to improve the other ones.
That's what it means. Yeah. Yeah, so that's what it means. And we will talk about it later. But we've hit a lot of terminology. We should relax and do some math. What's more relaxing than solving a math problem? All right. So, verify that x squared and 1 over x cubed are solutions to x squared y double prime plus 2xy prime minus 6y equals 0. And it says find the solution y, which satisfies y of 2 equals 10 and y prime of 2 equals 15. Okay, so let's start. So we're going to start with the verifying. So we've already talked about this, but let's remind ourselves, when it says to verify something, what do? We plug it in and see if it satisfies the relationship. So for x squared, what I want to check is x squared times the second derivative of x squared. So that's what this is. This x squared double prime means take two derivatives of x squared. Plus 2x times x squared prime minus 6 times x squared. Well, what does that work out to be? Well, let's work it out. Can we do two derivatives of x squared in our head? It's 2. Plus 2x, derivative of x squared? 2x. And then x squared, we'll just say x squared. So that's 2x squared plus 4x squared minus 6x squared, which equals 0. And so, aha, equals 0. Check. So we've now verified it. So that's our verification. Okay. Wow. See, in some sense, finding solutions are hard. Verifying, slightly less hard, at least if the functions are fairly nice. So the other function, 1 over x cubed, is the same as x to the minus 3. So I'm going to run through the same process. I'm going to take x squared times it by the second derivative of x to minus 3. Add that 2x times the first derivative of x to minus 3. Subtract 6 times x to minus 3. Well, this might not be quite so fast as the previous one, but it shouldn't be too bad. Okay, we certainly know the function is x to minus 3, so we can work our way up one layer at a time. What's the derivative of x to minus 3? Negative 3x to the negative 4. Right? What's the rule? Power comes down, subtract 1. So minus 3 minus 1 is minus 4. Okay. Now if I want the second derivative, I can take the derivative of the first derivative. 12x to minus 5. Yeah, people feel more confident after they've seen the one derivative. They're like, okay, I remember the rule now. All right, so what do we have? Well, x squared times x to minus 5 will give us negative 3. So 12x negative 3. Then the next term will give us minus 6x to the negative 3. Last term, minus 6x to negative 3. Put it all together, we get 0, which is what we want. So that's also been verified. Okay, so that's the first sentence. We're halfway done because there's only 2 sentences. Woohoo! Nice. All right, on to sentence number 2. So now we want to find the solution. And you might think, oh, man, we got to start from scratch, right? No. We've got 2 solutions. And we look at this and say, well, what kind of differential equation is this? What can we see? It's linear. It's linear and it's homogeneous. That says we have the principle of superposition. So what we can do is we can form new solutions by saying some constant times the first solution plus some other constant times the second. All right. So now we can say, well, look, maybe we just have to find a and b. Well, notice we were given information about y and y prime, so we should write down y prime. Now we know how to take these derivatives because we actually did it up here. So the derivative of x squared was 2x, and the derivative of x to minus 3 was minus 3x to minus 4, so we can just write those down without too much work. 2ax minus 3bx to minus 4. So plug in the initial conditions. And when we do that, it really says we're plugging in x equals 2. And we say that, okay, y of 2. So we plug y of 2 in. What is y of 2 in terms of a and b? 4a. Sorry, what? And 1 over 8. So x to the negative 3 becomes 2 to the negative 3. That negative 3 means it's downstairs, so it's like 1 over 2 cubed. So that's a 1 over 8. So I can write it as 1 over 8b. Do the same thing for y prime. Oh, and that equals 10. That's the punchline, equals 10. Do the same thing for y prime. All right, 2a times 2, 4a. How about this one? We have 3 times 2 to the minus 4. What does that become? 3 over 16. B. That equals 15. All right. And now we come to what I would call the bread and butter. The kind of thing we're going to do over and over again, the kind of thing that you need to get comfortable with because you are going to see it a lot. Definitely you're going to see it a lot in the upcoming homeworks over the next few weeks, where we have 2 equations and 2 unknowns. So how can we solve 2 equations with 2 unknowns? What's our approach? All right, lots of good ideas I'm hearing. Things like you have systems of equations, you've got substitution, someone said subtract, which subtraction here means elimination. And that's a great way to approach some of these problems, to say, can you eliminate one of the variables? Well, is there an easy way to eliminate one of the variables? Yeah, because these are both 4a's. So what we can do is we can take the second equation and subtract it from the first equation. You can think of it as minus 1 times the second equation plus the first equation. Well, 4a minus 4a goes away. Now, of course, the harder equation to do in your head. 1/8, then we're going to subtract negative 3/16. So it's like 1/8 plus 3/16 becomes 5/16. Oh, you guys are good. Equals 10 minus 15, negative 5. So now we have one equation and one unknown. That's a really good scenario. What does b need to be? Negative 16, yeah. Now we're not done because we don't have a. But once you know b, you can come back into, say, the first equation. And that becomes 4a. 1/8 times negative 16 is minus 2 equals 10. Which, of course, is the same as 4a equals 12. So what is a? A is 3. Great. Now, are we done? And why not? Yeah, we're not done because what do we need? We need the y. We need the solution. And so what we've done is we said, okay, y looks like this, and here are what a and b need to be, so we put it together. So our final answer is y equals 3x squared minus 16x to negative 3. And we're done. We've done what it's asked. All right, on to our next one. All right, so very similar. Verify that e to the x and x e to the x are solutions to y double prime minus 2y prime plus y equals 0. And find the solution y which satisfies. And here we get to pick some numbers. Let's pick some good challenging numbers to keep us on our toes. 17. All right. Good. These are the kind of numbers we want on an exam. 34. All right. Well, we should be able to finish that before class ends. Okay. So, we begin. Well, first we start with the verify. Same process. So, e to the x. All right, so we're going to check. When we take the second derivative of e to the x, subtract 2 times the first derivative of e to the x, add e to the x. Well, let's see what happens. What is the second derivative of e to the x? Yeah, that's why we like e to the x. E to the x, our old friend. The first derivative of e to the x. E to the x. The function e to the x. Yeah, it's e to the x. So we have e to the x, subtract 2 e to the x, add e to the x, put it all together, what do we get? 0. So this has now been verified. We ran it through. There's another function, x e to the x. But again, same process. We're going to take x e to the x, take the second derivative, subtract 2 times x e to the x, the first derivative, and then add just the function x e to the x. Now this one is probably not quite so fast to do in our heads, so we'll take our time and work up to it. So let's say we know the function. What's the derivative of x times e to the x? Okay, e to the x plus x e to the x. What rule is being used? Product rule. So you can think of it as take the derivative of the first times the second plus the first times the derivative of the second. All right. Now, what's the second derivative? Okay, so now we need to take the derivative of that. Yeah. So, yeah, someone was saying it's e to the x and then plus e to the x plus x e to the x. So we can put the e to the x's together, so 2e to the x plus x e to the x. All right, well, we hold out hope. So let's just, everything has an e to the x, let's go ahead and pull that out. So we'll have 2 plus x, and then we can remember that this minus 2 will distribute through, so minus 2, minus 2x, and plus x. So I'm just looking at the coefficients and gathering them together. Now, what do we look for? Cancellation. Okay. Let's see. The constants, we have 2 minus 2. Pew, pew. Canceled. How about the x's? X minus 2x plus x. Cancel. Pew, pew, pew. Now, you don't need to make the sound on the exam. You know, of course, people are like, oh, I know what problem they're working on, the one with all the pew sounds. Okay. So, we get 0, because everything cancels. This is 0 times e to the x, which is 0, which is what we want. So now this has been verified. All right. First half is done. Now begins the longer second half. Okay, so we say, look, same idea. This is a nice, in fact, this is really nice. Constant coefficients, it's linear, homogeneous, meaning we can apply superposition. It says, hey, we can find a solution which has to form some constant e to the x plus some other constant x e to the x. We just have to figure out what the right constants are for this to work. Well, all right, take a derivative. We know the derivative of e to the x is e to the x. We even know that this derivative, so, because we did it up here, where is it? Right there. And we can think of it as, if you factor out e to the x, it's like 1 plus x times e to the x. So, all right, as b times 1 plus x e to the x. All right, where do we plug in? 0. Hello, 0, our old friend. It's a great number. You've come to comfort us again. Y of 0 equals a and that's it, right? The rest goes away. That has to equal 17. Y prime is 0 equals a and b. And that has to equal 34. Now, 2 equations and 2 unknowns. I think we can solve this one. What can we see? Yeah, we definitely can see a is 17. So can we figure out b? Also 17. Now, I didn't pick these numbers. Somebody else picked it. Just a coincidence. So it won't always be the same number. So finally, to get our answer, we plug a and b back in. So we get y equals 17 e to the x plus 17 x e to the x. And we're done. Because we have a solution which satisfies our initial conditions. And really we know it's the solution because we know from our earlier statement that there's going to be only one. And so this is the one. Okay, now that we've had our light refreshing time doing some computations, back into a wall of text. Dun. All right. I know people are excited. They're like, ooh, I see linear algebra. Woo. Okay. Don't worry, we'll take our time here. Because this is an important concept. So remember we said that there's this phrase, linearly independent. We said that means fundamentally different. So we've got to come back and say, well, let's talk about how do we know? What does it mean? And so that's what this is going to do. So we say, okay, we're going to get into it. So again, the key phrase here is linearly independent. Now, if you look at the word independent, it means not dependent. All right, well, that's great. So what does it mean to be dependent? So linear dependence means that there's some way to combine these things together. So a constant times the first function, a constant times the second function, all the way up to a constant times your last function to get 0 in some sort of not good way. Now what's the good way? Well, there's an easy way for this to be true. Namely, if you put all your constants equal to 0, then definitely you get 0. So if there's a way to do it where some constants aren't 0, then that says, oh, these things are redundant. So let's look at an example. So let's suppose we take our first function, it's just the function 1, and our second function is the function x. So let's start with that one. So we're going to take c1 times 1 plus c2 times x, and we want to set that equal to 0. And the question is, does that mean that c1 has to equal 0 and c2 has to equal 0? Now keep in mind, this is for all x. Okay. Well, is it the case that both c1 and c2 has to equal 0? And how can we see it?
Because there's no way for the C1 term to keep up with the C2 term as x grows and shrinks.
All right. There's the rates of growth. That's sort of one concept. Let's use the fact that it has to be true for all x. What's a good choice for x? 0. So if it's true for all x, we have to have c1 times 1 equals 0. What does that tell us about c1? Yeah. X equals 0 tells us, oh, that tells us c1 has to equal 0. Okay, so we need c2 times x equals 0 for all x. Well, how can that be true? Now choose another choice for x, like x equals 1. What does that say about c2? That says c2 has to equal 0. So that says, look, the only way you can combine the functions 1 and x in a nice linear combination and get 0 out is this trivial combination where both c1 and c2 are 0. So we say these two functions are fundamentally different or linearly independent. Now let's do a different example. Suppose I give you the following two functions. y1 equals sine of 2x, y2 equals sine x cosine x. So, is there some way I can have some constant times sine of 2x plus some other constant sine of x cosine x and get 0 out? I can feel the energy of your 9th grade trig teachers are like, come on, you can do this. I showed you guys. Come on, guys, you can do this. Sorry, what?
Is it a C1 is double C2? Or is that around it?
Yeah, so it's actually very close. It's almost double. What are you thinking of?
I was thinking sine 2x is, I thought it was sine x cosine x over 2, but it might be more of that.
You're very close, yeah. So sine 2x is almost sine x cosine x. There's something called the double angle formula. So in particular, sine 2x is equal to 2 sine x cosine x. So if we make c1 1, and we make c2 minus 2, just because they're both on the same side so that they cancel, then what happens is you get 0. So what does this mean? Well, it's the double angle identity for sine, but what it really means, it says, if you tell me one answer is sine 2x, and then you say, oh, and another answer is sine x cosine x, I'll say, you haven't told me anything new. You haven't given me two fundamentally different functions. You basically gave me the same function twice, just written in a different way. So here, we would say these are linearly dependent. So, in other words, you didn't give me what I needed. We want independent. Okay, so that's sort of the notion of linearly dependent versus linearly independent. But how do we know? Because we are going to get into sort of complicated functions, and how can we know, be confident that what we have is independent or not? So this leads us into what's known as the Wronskian. Now, in case you're wondering, where does this name come from? It's named after a mathematician. They were a Polish mathematician. The ski in the name gives it away that it's a Polish name. So, what is the Wronskian? It's found in the following way. So we'll start with two functions. It says, okay, the Wronskian of two functions, you take the determinant. Now, depending upon how long it's been, you might remember what the determinant is, or you may have forgotten. At some point you've seen it, because it's a really important idea. So the determinant is a way to compute something from a matrix. You can think of a matrix as an array of numbers, or in this case, an array of functions. But it's really an array with benefits. There's sort of extra information that's stored into it. So in particular, what's the determinant? So if I have a 2 by 2 matrix, which I can write the determinant as, sometimes you see as det, determinant of this thing, or sometimes you just see bars here. What you do is you take the y1 times y2 prime, so you take the diagonal going down, and subtract the diagonal going up. That's for a 2 by 2. So y1, y2 prime minus y2, y1 prime. So in particular, the output is a function. So the Wronskian is a function. And at this point, you're like, okay, great. Well, how does that help us? Well, let's skip over the general statement and just come down here. It turns out that determinants are great at detecting linear dependence. So if you have things which are linearly dependent, the Wronskian will automatically be 0. There's just no chance. So in particular, if you compute your Wronskian and you get 0 out, you say, oh, there's some kind of linear dependence that I'm missing. So this is a nice check. But there's some other really nice fact which says, hey, if I have linearly independent solutions coming from a differential equation, in particular my linear homogeneous differential equation, I am 100% guaranteed that it's non-zero. So essentially, this is a great way for us to say, did we find our set of fundamentally different solutions that we need, or do we need to keep looking for more? So the Wronskian helps us make that decision. All right. Now, since we can do the Wronskian for 2 functions, we can do this quick example here. Compute the Wronskian for sine x and cosine x. Okay, so the Wronskian for sine x, cosine x, well, it's going to be a 2 by 2 determinant. The first row is the function, so it's sine x, cosine x. The second row, put in the derivatives. Derivative of sine is cosine. Derivative of cosine is negative sine. And now we take our determinant, sine times negative sine, so that's our going downhill, negative sine squared. Subtract cosine times cosine, so that's cosine squared. Minus sine squared minus cosine squared gives us negative 1, which is not 0. So that says, hey, sine and cosine are fundamentally different. They're not linearly dependent on each other. Now, that's 2 functions. What do you do if there's more? And the answer is, well, you just have a bigger determinant. So if you have a k different functions, you're going to have a k by k matrix full of functions. First row is just the functions. Second row, take the derivatives. What do you think the row after that would be? Second derivatives. You're cracking the code. Row after that? Third derivatives. And you just keep going until you fill up with all the derivatives. And then you take the determinant of that, and that's the Wronskian.